Hello YouTube! In this video we'll make our first synthesis. Here you see 0.2 grams of copper 2 sulphate pentahydrate. This is already a complex of copper with 4 waters. The fifth is in the crystal. The beauty of all transition metals is that they make complexes with very intense colors. Also, you can have one metal have many different colors depending on the ligands you put on the complex. So, to start the reaction, first we dissolve the copper 2 sulphate pentahydrate in 10 milliliters of water. As you see, it creates a very nice blue color solution, not really dark, but kind of sky blue color. Here you see the ligand we will use, which is called tetraIodoaniline, and is just one aniline molecule that on the opposite side of the amine group it has an iodine. This side is called para, so it's called tetraIodoaniline. To dissolve the tetraIodoaniline, we will use 10 milliliters of isopropanol. Also, we will use 0.7 grams of the tetraIodoaniline because that's what I had on hand. So to start with, we take with a pipette some isopropanol and we put it in the vial we have the tetraIodoaniline. As you can see, it dissolves in the isopropanol, but not very fast, so we will need to shake it after we add all the isopropanol. So, tetraIodoaniline is our ligand in this reaction. Ligands are molecules who have at least one lone pair of electrons. Since they have one lone pair of electrons, this side of the molecule where these electrons are is slightly negative compared to the rest molecule. So if there is around something positive, like a cation of a metal, then because of the Coulomb law, these two, the positive cation and the negative part of the molecule, must to have a force. At least they have two forces actually, and these forces bring them together because they move them. So when the ligand comes very close to the cation, it can take different geometries around it because many ligands come close, and for every cation, we have different number of ligands that can get close and take a shape which is actually a special type of ionic bond, or so the crystal field theory says. We will use the crystal field theory to explain the color of the copper complexes, but we'll talk about this in the theoretical videos. Here we'll just make a synthesis. The geometry of the product is square planar, with the copper on the center and 4 tetraIodoanilines in every corner. So here you see our reactants and the reaction vessel. Here we will do the reaction. This vial is very small, only 50 milliliters. On the middle you see the solution of the copper 2 sulphate pentahydrate with a very nice blue color, and on the left you see the solution of tetraIodoaniline on isopropanol. Now time for some theory. Here you see the 5 3D orbitals of the copper metal. They look kind of complicated, but they actually are more complicated if you try to describe them with mathematics. If you stay in the shape of them, I think it's kind of easier to comprehend them and remember them like this. So there are 5 of them, and all transition metals have them, and not only the transition metals, actually all atoms who have the n quantum number bigger than 3, they have them, and more of them. If you see them separate, they look like this. The blue indicates the minus sign of the wave function, and the yellow indicates the plus sign of the wave function. The wave function describes the amplitude of the probability to find a quantum particle, like an electron, in some place. And not only that, we can have momentum wave functions and many kind of wave functions in quantum mechanics, but mostly these, they describe the probability for something we want to see. So copper have some of these, since it has an electron configuration that in the neutral state, all of them, they are full, and also there is one more electron in the 4s orbital. So you can see now that the neutral copper has the configuration on above, while when we take 2 electrons from copper, we make the electron configuration that is under. So you can see that in the electron configuration that is under, copper have one non-paired electron, while on the above, all of their electrons, they're paired. So we can have a transition, but the problem is that all of them, all of the 3d orbitals still have the same energy. If we put ligands around the copper, and ligands are negative charges, we can see that if we make a square planar configuration, if we put 4 ligands, they must be face to face with the dx in the square minus c in the square orbital of copper. So the negative charge on the ligands repels the electrons in these orbitals, and they must go very high in energy. Also, the dxc orbital, which is very close to this orbital in geometry and in space, must also go kind of high in energy, but not as much as the dx in the square minus c in the square orbital. So if we see, after we put the ligands, the energy of the orbitals is splitted. Some of them have less energy, some of them have more energy, and as you can see in the symmetry we have, which is square planar, we have at the top the dx in the square minus c in the square as predicted, under it the dxc, which is also predicted, but we can see that we have the dz square above the dpz and xz. This happens because the dz square have a donut, which is in the xc plane, and this means that if the electrons, they are there in the dz orbital, then they must also feel kind of repulsion from the ligands electrons. But now we see that the energies of the orbitals are splitted. So one electron from the lower energy orbitals, it can absorb a photon from the white light that comes from our lamp or from the sun, and when it absorbs it, it will jump to the dx in the square minus c in the square orbital, which is the highest energy orbital, and if it has the right spin orientation, it can pair with the unpaired electron that is in this orbital. These kind of absorptions, they are called dd transitions, and these give the color to the complexes. So when the electron absorbs a photon from the sun or from the lamp, this energy from this photon corresponds to a color. So this color is removed by the spectrum, and what is left is the complementary of it, which actually reflects to your eyes, and this is the color you see in any color around you actually, but all colors around you just may have different kind of transitions, but most of them work like this. So enough with the theory and let's get started. On the right you see in the reaction vessel the blue solution of copper 2 sulphate pentahydrate. On the left you see the solution of 5-iodoaniline in isopropanol. Now all we have to do is mix these two, and before this we will put the vessel on the hot plate. The reaction that will happen is a ligand exchange between the waters and 4 iodoanilines. The molecule is square planar as you can see and will have a very strong change in color, which will indicate that the reaction happens. So here we have the copper solution, and we bring the 5-iodoaniline, or the para-iodoaniline actually. And with a pipette, we will put drop by drop the solution of the para-iodoaniline to the reaction mixture. Watch closely because it's gonna be fast. Here we put some. Alright, you can see very fast change of color. It goes from a very nice blue to a very nice orange to orange gold color, which is strange for copper complexes, except the oxide of course, which is red. Copper usually make more blue or violet or green complexes, so it's kind of strange for me to see a color like this, but this means that the ligand changes the energy between the orbitals differently than the ligands that I'm used on zinc, but it's very beautiful as you can see. Now we put the last of the para-iodoaniline. We wash the vial with small amounts of water and we put it back in the mixture. We have actually a 50% solution of water and isopropanol in there, so this will keep the para-iodoaniline kind of soluble and also kind of soluble the copper salt. But as it seems, the complex that we make in the end is very not soluble in water and also slightly soluble in isopropanol, so it crystallizes out very fast, as you can see. Here maybe you can see better the completely different color we have now. And also I wear different gloves because some of the product fall on my hands and I had to change the gloves. So here we put some water to make the product crystallize out, and it was a success. product is not soluble in water, which is uh, very logic if you think it, because okay, from the one side is a salt, from the other side the one part of the salt, which is the cation, which is our complex of copper with the 4 para-iodonylines, and it has 4 benzene rings, and also actually it has 4 para-iodonyline, and para-iodonyline is not anyway soluble in water, so 4 of them must kind of make the cation hydrophobic. So we have a hydrophobic cation, which is very interesting. So now it's time to filter our reaction mixture to collect the crystals we just made. So put on your vacuum and filter. Wash the vial with some water and put the rest of the solution inside the filter. This way you will have smaller loss. As you can see, the filtrate is very clean, which indicates that no copper ions are in there, or not many at least. Time to wash it with some isopropanol. So wait until it gets dry, after collect your crystals, and of course not forget to clean your filter, which is a pretty easy job actually. You can just use hydrochloric acid and after some water, and you will make again one complex of copper with chlorides, and also the aniline that is produced, or the para-iodonyline, which is kind of the same, will get protonated, and this will make them very soluble, and this way you can clean your filter very easy, because as you see now it's a big mess in there. From the other side, the filter rate is very clean, so this is how clean is our filter after this hydrochloric acid and after deionized water. So let's take a look in our product. Here we have our dry product, which is 0.37 grams, which indicates a yield of around 45%. Not bad for so small, for the small amount we use. So that's it. Thanks for watching, and see you again in the next video. And don't forget,